Good afternoon. My name is Hyungyap and I'm from Kyung University. Today, I'm going to present our research, SafeXR, alerting working persons to obstacles in mobile XR environments. First of all, I would like to tell you the motivation behind the research. The performance of smartphones has evolved so rapidly that people can now enjoy a variety of XR applications with their smartphones. These days, we can often see people using the XR application on the street. However, use of smartphones while walking compromises pedestrians' cognitive resources. This is mainly due to the multitasking competition of limited cognitive resources. When a smartphone task is added to the walking task, one's spatial awareness of the surrounding environment becomes distracted and can compromise their safety. Then, the users may run into obstacles ahead in the path. As a solution to this issue, we propose a safety assistance system to notify mobile XR users of obstacles ahead in their path. We name the system SafeXR. Then, we optimize the SafeXR for users in various mobile XR environments. To this end, we conduct a preliminary test and 3 experiments with mobile games. The obstacle detection is achieved by using smartphones' built-in sensors. We first used the visual inertial odometry functions and extracted 3D feature points from the input camera image. Then, we classified the feature points into 2 groups, ground feature points and out-of-ground feature points. If the out-of-ground features are close to each other and their counts exceed the predefined threshold, we judged that the features make up an obstacle. Using the obstacle detection technique presented in the previous page, we developed a prototype of safety assistance system for walking persons. It provides an alert when obstacles are detected ahead in the walking path. With the prototype, we conducted a preliminary test to investigate what kinds of improvements were needed. In addition, we also investigated how it could be optimized for various mobile environments. The test was made in 3 environments: SG, typical smartphone gaming; AR, AR gaming on a smartphone; and VR, VR gaming with a mobile head-mounted display. For the test, we recruited 10 participants aged between 23 and 30. Playing the shooting game, the participants freely walked in an indoor area. In the walking areas, we placed the soft cubes made of foam rubber. We tested 3 alert interfaces, each of a single modality. The screen color changes as a visual alert, a siren as an auditory alert, and vibration as a tactile alert. Through the preliminary test, we identified 2 major issues to be investigated further. The first is when to alert the walking persons to the obstacles ahead. In our prototype, the alert was given when the distance to an obstacle became 3 meters or shorter. However, some participants complained about the alert timing. We observed that the preferred alert timing seemed to depend on both walking speeds and the mobile environments. The second issue is how to deliver the appropriate level of urgency to users. Participants disliked the alerts when they conveyed unnecessarily strong urgency. We observed that the preferred urgency seemed to depend on the distance to the obstacles. To resolve these issues, we conducted 2 experiments. Through the experiment 1, we first investigated when to alert the walking persons to the obstacles ahead. If the alert is given too late, our safety assistance system is useless. In contrast, if the alert is given too early, it will unnecessarily draw the user's attention. The experiment was conducted with mobile games because the problem of compromised safety is aggravated during the task of playing games. As a game, we implemented a trail making test. It displays a set of numbers and letters and then asks the user to select them one by one in the alternating order of numbers and letters. The test was made in 3 environments. As in the preliminary test, we tested in SG, AR, and VR environments. Participants were asked to walk straight while playing the game. In SG and AR, pink line on the ground guided the user. In VR, virtual penguin guided the user. For the experiment, we recruited 20 participants aged between 22 and 32. Playing the TMT game, participants walked a 12-meter-long straight path, avoiding an obstacle in the middle. At the end of the path, they were asked to choose whether the alert was given too early or too late. In SG and AR, we used an auditory alert. In VR, we used a visual alert. We tested 3 different walking speeds, 0.5, 1.0, and 1.5 meters seconds. We tested 7 alert distances, 1 to 4 meters. We have 21 combinations and each combination is repeated 5 times. As we tested 3 mobile environments, each participant performed 315 trials in total. The analyzed results are shown in the figure below. The data were fitted with the sigmoid function, the x-axis for the 7 alert distances, and the y-axis shows the probability of considering the alerts too early. Then we defined D, which is the most desirable and preferable alert distance, as the alert distance that has 50% probability to consider the alert early. The values of D shown on the table are fitted with the polynomial function. We subsequently divided it by the walking speed to obtain the time to collision, TTC. TTC refers to the time required for a person to collide with the obstacle when the current speed is kept. In all mobile environments, participants prefer to be given an early alert when they walked fast. We hypothesize that this is mainly because people tend to maintain a certain TTC. However, when the walking speed is slower than 1 meter per sec, TTC sharply increases as the walking speed decreases. We speculate that this is related to the concept of personal space, a protective space maintained around the body during the walking. We observed that even when participants walked very slowly, they felt uneasy as the obstacles were too close. Through the experiment 2, we investigated what kind of interface is appropriate for alert working persons. The test was made in 3 environments. With walking speed fixed at 1 meter per second, we used the most preferred alert distance D identified in E1. As in E1, TMT game was used. For the experiment, we recruited 20 participants aged between 22 and 32. Taking levels of our alert urgency into account, 4 types of interfaces were presented and compared in each environment. Based on the preliminary test results, 4 types of auditory alerts were designed and tested in SG and AR. Table shows one-time sound, regular sound, graded sound, and constant sound. In VR, 4 types of visual alerts were tested. Table shows one-time points, regular points, graded points, and constant points. The example of the red points are shown in the figure below. In SG and AR, the participants are instructed to keep walking for 3 minutes along the edges of the rectangular area. In VR, participants are instructed to walk for 3 minutes within the area. In Experiment 2, participants performed 12 trials in total. After trial, the participants filled out a subjective evaluation questionnaire shown in the table. We assume that the user experience is better as the awareness score is lower, the task attention score is higher, and the feeling safe score is higher. After testing all 4 interfaces in a mobile environment, participants were asked to score their preferences for each interface in the range 0 to 100. In all mobile environments, participants often miss the short alert of one-time sound and one-time points. This made them feel unsafe and also pay more attention to the surrounding environments. In all mobile environments, GS generally showed the highest scores in task attention, feeling safe, and preference. As GS conveyed the additional information about the distance to the obstacles, the GS seemed to be more trusted. The goal of Experiment 3 was to investigate SafeXR's contributions to the user safety and task performance. The test was made in 3 environments. We designed 2 test cases, one with SafeXR and one without SafeXR. Participants were instructed to freely walk at their natural speed. We used the most preferred alerting distance D identified in E1. As an alert interface, we used the graded sound GS for SG and AR and the graded points GP for VR environments. As in E1 and E2, TMT game was also used. For the experiment, we recruited 12 participants aged between 12 and 30. We used the same task as used in E2. In FG and AR environments, the participants are instructed to keep walking for 3 minutes along the edge of the rectangular area. In VR, participants are instructed to walk for 3 minutes within the area. In Experiment 3, participants performed 6 trials in total. The task performance was evaluated in terms of 3 items: game progress, miss ratio, and average time between hits. Our analysis found that SafeXR had no effect on task performance in SG, whereas SafeXR increased the task performance in AR and VR. After trial, the participants filled out a subjective evaluation questionnaire. After testing all 4 interfaces in a mobile environment, participants were also asked to score their preference for each interface in the range 0 to 100. They were asked twice, if your priority were on completing the task, how much would you prefer the alert? And if your priority were on ensuring safety, how much would you prefer the alert? In SG, SafeXR made participants become less aware of the surrounding environments and feel safer. When their priorities were on the games, they did not seem to care whether the alerts existed or not. When their priorities were on the safety, however, they preferred playing games with SafeXR. In AR environments, SafeXR made participants pay more attention to fulfilling the task and feel safer. As in SG, participants preferred SafeXR only in safety first. In VR environments, SafeXR made participants become less aware of the surrounding environment, pay more attention on tasks, and feel safer. Participants preferred SafeXR both in task first and safety first. In this study, we presented a safety assistance system named SafeXR. Its purpose is to notify the users of the obstacles ahead while they are walking. To optimize the system for various mobile environments, we conducted 2 experiments and applied the results to our system. Then we conducted an evaluation test and found that SafeXR successfully increased user safety, improved task performance, and enhanced user experience in mobile XR environments. Thank you for watching, and this is now time for 10 minutes questions.